Hi friends, welcome to the another lecture on the theory of semigroups. In the last lecture we have discussed about zero element, identity element. Also we have mentioned the idea of adjoining identity element to a semigroup whenever necessary. So in this lecture we are focusing on the properties of zero element, adjoining zero element, and some other notions. So first thing I want to recall is zero element. Zero element. Zero belongs to S is a zero element if for every S belongs to S we must have 0 times S equal to 0 equal to S times 0. So the very important fact is when you multiply with zero element you will get 0 only. So this is the basic property of a zero element. As we have seen, the identity element, when you multiply it, you will get back the element which you have multiplied to the identity. So these are the basic properties of identity element and zero element. Now, as we have seen in the case of identity element, we could prove that S has at most one zero element. So one observation, S has at most one zero element. For this, we can suppose that 0 and 0 prime are zero elements of semigroup S. Then 0 dash equal to 0 times 0 dash. This is because 0 dash is a zero element. Because whenever you multiply with the zero element, you will get back the zero element. So since 0 prime is zero element, when you multiply it with another element 0, you will get 0 dash. But you also know that 0 is a zero element, then 0 times 0 dash again going to be 0. This is because 0 is a zero element. It's the same technique we have used in the case of identity. That is 0 prime equal to 0. That is 0 element is unique if it exists. Second thing we must observe is whenever we say that S has 0 element, we must emphasize the cardinality of S. That means S must at least contain two elements. That is, S must contain at least two elements. Why? Suppose S has only one element, let us call some E. Then we know that to become a semigroup you need to have a map, right? S cross S to S. So what is the only map available? The only map available is EE is going to the element E, or in the multiplication sense, E square equal to E. That means E multiplied to E, we got E itself. This is a property of a zero element. When you multiply with an element, you are getting the element, then what is the this would be a zero element. So a singleton set, a singleton or semigroup always contains a zero element. So there is no need to mention it as a zero element. There is no idea to adjoining and everything else. So whenever we define zero element, the S must have at least one element. Okay. So maybe we can think about, is this semigroup contain identity element? What is the property of identity? When you multiply with the identity, you will get the element, right? But that also happening here, right? When you multiply with E is multiplied with this E, you getting the same E. That means E also can be worked as an identity. It is a zero because you are getting E itself, right? So you understood. So this singleton set semigroup all contains identity and a zero element. So there is no point of just discerning these two things from the semigroup containing one element. Okay. So the next thing is, if a semigroup does not containing a zero element, then we can adjoin a zero element. So the next thing is, we are going to adjoin a zero element. Adjoining zero element. If S is a semigroup without zero element, we can adjoin zero element to S by defining two conditions. As we have defined identity, we have to define for every S in S, S times 0 equal to 0 equal to 0 times S. Second thing, what is the product of 0 times 0? It also 0. So by S power 0, what we mean by this, either S is a semigroup with zero element, or S union 0 as described above. Either S contains naturally a zero element, or we can adjoin 0 to a semigroup, which is S union 0. So there are many examples where the containing zero element. We have already seen such examples in the last lecture. So the next thing we have to see is, if a semigroup does not containing a zero element or identity element, we could actually adjoin zero element and identity element. But the whole theory of semigroup cannot be reduced to semigroups containing zero and one zero element and identity element. We will see why this. For example, we know that all groups are semigroups, right? A group is a semi-group having extra conditions. So if you adjoin 0 to a group, it can remain as a group again. So this is an important fact that we must know. We will prove that. The fact is, if we adjoin 0 to a group, it can't remain as a group again. That is, when you adjoin 0 to a group, it will be a semi-group, but it cannot remain as a group. So it actually changes the properties or changes the structure of the semigroup, right? So how do we give an instant proof to this claim? So let us just write it very clearly. A result if G is a group having, if G is a group having more than one element, then G can't contain a 0 element. That is, if G, the cardinality of G is greater than 1, then G cannot contain a 0 element. So we will definitely prove this by a certain contradiction. So assume that cardinality of G is greater than 1. Suppose G contains a 0 element. Suppose that G contains a 0 element, right? So then we are going to see what is the problem. That means 0 belongs to G. So now G is a group. Since G is a group, 0 has an inverse, right? So 0 has an inverse in G, say 0 prime. So what the inverse will do? Definitely G has an identity. So 0 times 0 dash would be 1. Here 1 is the identity of G. So 0 times 1 means the operation you are giving, then you get 1. But you know that 0 is a 0 element. 0 is a 0 element. What is the property of 0 element? When you multiply with any number, you will get 0. So 0 times 0 dash would be 0. This proves from the both equations we will get 1 equal to 0, that is identity element 1 equal to 0. The identity and 0 element are same, or I can say that 1 is a 0 element, right? The 0 element we have found in the group was actually the identity. Now what is the problem here? This implies for every G in the group, we know that G times 1 is G, and G times 1 can be written as G times 0. Since 0 is a 0 element, you will get this is 0. That is, for every G, what happens? G equal to 0. That means how many elements are there? G is only contain 0 element. Symbolize cardinality of G equal to 1. Which is a contradiction to the fact that cardinality of G greater than 1. Okay, so this is why we can say that if G is a group having more than one element, then G cannot contain a 0 element. So adjoining 0 to a group will definitely spoil its structure of being a group. Okay, the next thing is actually the beginning of the semigroup. We start with something called left 0 semigroup and right 0 semigroup. So left 0 semigroup and right 0 semigroup. Okay, so let S be a semigroup. We define a multiplications. We define a multiplication star as follows. So star is a binary operation on the semigroup, and we define like this: for any x, y belongs to the semigroup, x, y equal to x. That means when you multiply two numbers, you will get the left number as a result. So we know that what is the property of a 0 element in a group? When you multiply with a 0 element, you will get the 0 element. So that is a two-sided property. But here we can see that x times y, you are getting x. That is when you multiply by the left of a number, you are getting the same number. So it is more or less similar in the definition of 0 element. That's why it is called left 0 semigroup, and we can see that this is in fact a semigroup. How do you prove that it is a semigroup? We must prove that it is associative. To show associativity, we took any three numbers in the semigroup x, y, z, and we calculate x times y, z. This would be x, because as per our definition, you will get the left number. Now we can look at what happens x, y, z. You will get the number in the left as in the bracket, that would be xy. But you know that xy will be again going to be x. That is x times y z equal to xy times z. So this multiplication is valid, and this multiplication is associative, and that means it is a semigroup. So we call this semigroup, we call this as left 0 semigroup. So the right 0 semigroup can be defined similarly. We define for any xy belongs to the semigroup, we define something like this: y x equal to x. In this case, when you multiply two numbers, you will get the right number as a result. Okay, so when you multiply with the number, you are getting the right number. It's similar definition as in the definition of 0 element. So Also you can check that this is also associative in this manner. So this is a semigroup. We call it, the semigroup would be right zero semigroup, right zero semigroup. Now we are going to see, is there any way that we can produce this right zero and left zero semigroup from any other means? That is, we are going to study about what is called rectangular band. So next thing is, we are going to study about rectangular band. Rectangular band. For rectangular band, let us choose I and lambda be two non-empty sets. Then I cross lambda is a basic Cartesian product of two sets. I cross lambda will be a semigroup under the operation I lambda times j mu equal to I mu. So look at the definition, right? In I cross lambda, what we have to define? We have to define a multiplication star from where to where? I cross lambda cross I cross lambda to I cross lambda. That's why each entry are like two tuples or ordered pairs. So this is coming from I cross lambda. This is coming from I cross lambda. That means I is belongs to I, and j is belongs to I. We have lambda is belongs to capital lambda, and mu is belongs to capital lambda. So if you define a multiplication like this, definitely you can prove that this is an associative operation. So that would be left as an exercise. It is very easy to check. The main important thing is we are going to see what if capital lambda is a singleton set lambda, small lambda. Then how do we define the multiplication rule? So this we can see that then I is any set, but the lambda is a singleton set. Capital lambda is a singleton set. Then the multiplication would be I lambda times j. We don't have a mu. We have lambda itself. Lambda. You will get the first entry of the first element and second entry of the second element. That means you will get I lambda. So what is actually we are getting, this multiplication rule is actually automatically converted into the multiplication rule in left zero semigroup. Correct? So you are getting the left element when you multiply with this. So this actually defines a left zero semigroup, LCS. So when capital lambda is singleton, I cross lambda will be a left zero semigroup. What happens if the cardinality of I is the single I? Then the multiplication rule, let us look at the multiplication rule. I lambda times, there is no j, only I out there. I, there may be a mu, right? The rule would be I mu. You can see that we are getting the right member as a result. That is, it is similar to the multiplication rule in right zero semigroup. So when I is singleton, you will get I cross lambda as a right zero semigroup. So note that in I cross lambda, if lambda is singleton, that means the right member in the Cartesian product is singleton, means you will get a left zero semigroup. A left member of set I is singleton means you get a right zero semigroup. So there is some kind of inversion is there. Okay. So next we are going to see a very important semigroup, the power set of a semigroup. So power set of semigroups are the collection of all subsets of a semigroup in our hand. So let us define the power set of S is nothing but a set of all subsets of semigroup. We will prove that this is in fact a semigroup. So the power set of S can be a semigroup by defining certain multiplication. So we define mu like from power set of S cross power set of S to power set of S as follows. Mu of AB, that means A is a subset of a semigroup, B is also subset semigroup. We define something like this. The product of two sets again is defined as AB belongs to the semigroup such that A belongs to A and B belongs to A. You select all elements in A and select all elements in B, then you take the products. This would again going to be a subset of the power set of subset of semigroup, an element of power set of S. So this is well defined. So the associativity can be easily checked. For example, what do we have to prove is for any three subsets of the semigroup, we have to prove that this is actually equal. I'll prove the left inclusion, the right inclusion is similar. Let's look at Y belongs to ABC. This implies there exists a Q in AB and there exists a C in capital C such that Y equal to QC. But you know that Q belongs to AB means there exists A belongs to A and B belongs to B such that Q equal to AB. This implies Y is equal to ABC, right? These A, B, C are coming from where? The semigroup. So associativity is there. Then we can write A times BC. This in fact proves that Y belongs to A times BC. So this is actually proves one inclusion. AB times C is a subset of A times BC. In similar way, you can prove that A times BC is a subset of AB times C, which proves our claim. Okay, so we have proved the power set of a semigroup is again can be viewed as a semigroup by defining the product of two subsets of a semigroup. Okay, so by this result I am concluding my lecture. In the next lecture, we will see some more aspects and some more notions of semigroup, and we will slowly develop our theory to fruitful nature. Thank you.